Welcome back to the deep dive. Today we are examining a piece of research that fundamentally tries to change the relationship between a 2D image and 3D space.
It's a really big goal.
The paper is called SAM3D, 3Dify Anything in Images, and it's coming out of Meta Superintelligence Labs. The basic promise here is pretty stark. Take a single real-world photo, clutter and all,
Yeah.
and pull out a complete 3D model.
Not just the shape, but the texture, the layout, everything. The researchers are really trying to break down what they call the 3D data barrier.
Right, because for decades, getting a machine to see volume from flat pixels has been, well, a huge struggle.
It's because machines don't instinctively get that a 2D image is just one perspective of a 3D world. The paper makes a great point about how we humans do it. We use what they call pictorial cues.
So when I look at a picture of a chair, I don't need to see it from all sides to know it has four legs and a back.
That's it. You use shading, texture, but most importantly, use recognition. Your brain says, that's a chair, and it pulls up a mental model of a chair to fill in the parts you can't see.
And SAM3D is trying to mimic that exact process. Use recognition to drive the reconstruction.
And not just guessing the visible surface, which is sometimes called 2.5D. This is about generating the full, complete 3D shape so you could, re-render it from any angle you want.
So let's talk about that barrier you mentioned. The core problem they identify is a lack of data.
It's a huge data scarcity problem. We have billions of 2D images. We have lots of 3D models. But we don't have them paired up, especially for messy real-world scenes.
And that's why older models struggled.
Right. They were trained on what the paper calls isolated objects. Think of a 3D model of a sofa just floating in a white void. The model gets really good at seeing sofas in white voids.
But show it a real living room with a blanket thrown over the sofa and weird lighting.
And it just falls apart. It can't handle the occlusion, the clutter. So the Meta team knew they couldn't just find this data. They had to create it.
Which brings us to their training recipe, which they say is inspired by how large language models are trained.
Yeah, it's a multi-stage process. Pre-training, mid-training, and then post-training.
Okay, let's start with stage one, the pre-training. The paper says they used a dataset called ISO 3DO.
This is all about learning a basic vocabulary of shape and texture. It's built from about 2.7 million synthetic 3D meshes from big libraries like Objaverse XL.
So just pure, clean 3D models.
And they render each one from 24 different viewpoints. The goal here isn't scene understanding. It's just to teach the model the fundamentals of geometry, what a sphere looks like, what a cube looks like.
Then we move to what they call stage 1.5, or mid-training. This is where it starts to get really clever with a data set they call RP3DO.
RP stands for render paste. This is the bridge from that clean synthetic world to the messy real world.
So they're literally pasting these 3D objects into real photos.
They are, but it's more than a simple copy-paste. They use a couple of smart tricks to force the model to learn. The first is called flying occlusions.
Which sounds exactly like what it is.
It is. They just randomly insert other objects in front of the target object. This blocks the view and forces the model to learn shape completion. It has to guess what the rest of the chair leg looks like, even if a sphere is floating in front of it.
It learns that objects continue even when you can't see them.
Right. And the second trick is object swap. This is for getting the context right.
Okay, how does that one work?
The system finds a real object in a photo, say a lamp, and then digitally replaces it with a similar synthetic lamp from their library. But it maintains the depth and contact points so it looks physically correct in the scene.
So the scene looks real, but for that one object, they have perfect 3D ground truth because they put it there.
And that's the key. But even with all this, it's still training on synthetic things placed in real images.
Which leads us to the final stage, stage 2, post-training. This seems to be the heart of the paper, the model in the loop pipeline.
I would say so. This is their big insight for data collection. They realize that humans are, pretty slow and bad at making 3D models from scratch.
Yeah.
It takes hours.
But we're incredibly fast at judging them. We can look at a model and know instantly if it's right or wrong.
And they built a whole system around that idea, a data engine. The first step is that a human annotator looks at a real photo and just masks out an object they want to reconstruct.
Okay, so they pick the target, then the model gets to work.
Then the model generates a bunch of different 3D candidates, let's say 8 of them. This is the ranking and selection part. The human just acts as a judge. They look at the 8 options and pick the best one.
The best of N approach.
And there's one more step, alignment. The annotator then takes that chosen 3D mesh and uses a tool to rotate it, move it, and scale it so it fits perfectly into the 2D photo.
So they're locking the 3D shape into the 2.5D scene.
That's a good way to put it. Now, sometimes the model just fails. All 8 options are bad.
The paper called these hard examples.
Right. And when that happens, the image gets sent to a different group, professional 3D artists. They build the 3D model from scratch. It's expensive, but it seeds the model with high-quality data for really tough cases.
And the result of all this was a pretty massive data set.
Unprecedented, really.
Yeah.
Almost 1 million images paired with over 3 million untextured meshes and about 100,000 textured ones. Nobody has had in the wild paired data on this scale before.
So with all that data, let's look at the model architecture itself. How does SAM 3D actually think? The paper says it's split into 2 parts.
Yeah, they broke the problem down. First, there's the geometry model. It uses something called a mixture of transformers, or MOTI,
And its job is?
to predict 2 things at once: the rough, coarse shape of the object in voxels, and also its layout, the rotation, translation, and scale.
It figures out the what and the where simultaneously, and I think the paper also mentioned it can use optional inputs.
It can. If you have, say, a point map from an iPhone's LiDAR, it can use that. But it works perfectly fine with just the standard RGB image.
Okay, so once you have that coarse shape,
It gets passed to the second component, the texture and refinement model.
this sounds like where the detail work happens.
It is. This part uses a sparse latent flow transformer.
Hmm.
It takes the blocky voxel shape and refines it, smooths it out. And at the same time, it paints the texture on.
And it's not just stretching the visible pixels over the shape, right?
No, it actually hallucinates the texture for the parts you can't see based on what it can see. And to understand all this visual information, both the object and the scene.
They use Dino V2 as the image encoder.
Right. It extracts features from the cropped-in object for the fine details, but also from the whole image to get the context, like lighting and perspective.
So let's talk performance. How do you even measure if a 3D reconstruction is good?
That's a classic problem.
Yeah.
So to solve it, the researchers actually built a whole new benchmark for this paper called SA3DAO.
SAM 3D artist objects.
Exactly. It's 1,000 real-world image and 3D mesh pairs, all made by professional artists. And they specifically picked diverse and tricky objects, things like ski lifts, churches, even tribal masks.
And how did SAM 3D do on this benchmark?
It performed very well. In tests where humans were asked to pick the better reconstruction, SAM 3D had a 5-to-1 win rate against the previous best models, like Trellis or Hunyuan 3D.
And the biggest difference was in those cluttered, occluded scenes we talked about earlier.
That's where it really shined.
Yeah.
Where other models would just leave a hole or create weird floating bits where something was blocked, SAM 3D was much better at inferring the complete shape.
The paper also mentions an improvement in efficiency.
Yeah, they use a technique called distillation. Generative models like this often need a lot of steps to produce a result. They managed to cut the number of inference steps from 25 down to just 4.
Which makes it much, much faster without losing too much quality.
And that's critical if you want to use this for things like AR or robotics.
Which is where the paper concludes, right?
Yeah.
Pointing towards those applications.
Yes, the authors are very clear. They see this unlocking new capabilities in robotics for navigating cluttered spaces and in AR/VR for making virtual objects interact realistically with the real world.
The final thought in the paper's discussion section is really interesting. They circle back to this idea that recognition enables reconstruction.
It's really the core thesis of their whole approach. The model proves that even if it's never seen a specific object before, like a one-of-a-kind sculpture,
It can still reconstruct it.
it can, because that sculpture is made of parts, curves, surfaces, textures that it has seen before in other objects. It builds the new unknown thing from a vocabulary of known things.
It builds the unknown from the known. That covers our analysis of the SAM 3D paper. We will see you on the next deep dive.